A risk monitoring system for financial markets is proposed, leveraging big data and machine learning technologies to enhance efficiency and accuracy in risk management. The system's architecture consists of 4 layers: data, computation, application, and presentation. The data layer aggregates raw financial data from diverse sources, including transaction records, market indicators, and news reports. In the computation layer, machine learning algorithms such as long short-term memory networks, random forest, and gradient boosting trees process and analyze the data, extracting valuable information and capturing market dynamics. The application layer performs risk assessment and generates alerts based on the computation layer's outputs, supporting decision-making for financial institutions. The presentation layer visualizes the analysis results through a graphical user interface, enabling users to intuitively understand the risk situation. The system's design ensures efficient management and real-time processing of data flows, allowing for swift responses to market changes. This is achieved through the integration of large-scale financial data and advanced machine learning algorithms, including the real-time data processing platform Apache Flink. Research findings demonstrate that the system significantly enhances efficiency and accuracy in risk management, particularly excelling in identifying and warning against market crash risks. By leveraging big data and machine learning technologies, the proposed system provides a robust and accurate risk monitoring framework for financial institutions, enabling timely decision-making and risk mitigation strategies. A risk monitoring system's architecture is designed to collect, pre-process, and analyze financial market data for risk identification and assessment. The data collection and pre-processing module aggregates data from multiple sources, including market transactions, macroeconomic indicators, and news media information. Rigorous pre-processing steps, such as data cleaning, normalization, and feature extraction, ensure data quality and consistency before entering the computation layer. The Risk Identification and Assessment module employs deep learning models, specifically long short-term memory, LSTM, networks, to capture long-term dependencies and complex fluctuations in financial time series. LSTM models utilize gate mechanisms to control information retention and forgetting. The forget gate, input gate, and output gate optimize the model's memory capacity for time series analysis, influencing the final output. Equations govern the operation of these gates, determining which information to discard, store, or use for computing the next hidden state and output. LSTM models process data through a series of iterative computations, where each gate's activation is determined by a set of learned weights and biases. The forget gate, FT, is computed using the sigmoid function, sigma, WF, XT plus UF, HT1 plus BF, where WF, UF, and BF are learned weights and biases. The input gate, IT, and output gate, OT, are computed similarly. The final output is generated by the LSTM network's hidden state, HT, and output gate, OT. The use of LSTM networks enables the risk monitoring system to capture complex temporal relationships in financial time series data, facilitating accurate risk identification and assessment. The authors of the research paper present the mathematical formulation of the long short-term memory, LSTM, network, a key component in the risk monitoring system. This network is defined by equations for forget, input, and output gates featuring IT and OT respectively. These gates are computed using the sigmoid function sigma and weight matrices WF, WE, and WO, along with bias terms BF, BI, and BO. The cell state quart and hidden state HT are updated based on the previous hidden state HT1 and input XT. The warning and decision support module is a critical component of the system, generating risk alert signals based on the risk assessment results from previous modules and providing real-time decision advice. This module utilizes Bayesian decision theory to optimize warning thresholds, ensuring the timeliness and accuracy of alerts. The specific formula for Bayesian decision theory is P, A, B, equals P, B, A, times P, A, phosphorus monoboride, where A represents a risk event and B represents observed market signals. The system implementation is described, focusing on the construction of a big data processing platform based on the Hadoop ecosystem. This platform uses HDFS for storing large volumes of financial market data and Apache Spark for efficient data processing and complex computations. The platform also integrates other Hadoop ecosystem components, such as Hive and Pig, supporting complex data querying and analysis tasks. The selection and implementation of machine learning algorithms are discussed, with three primary algorithms chosen for risk identification and assessment: LSTM, random forest, and gradient boosting trees. These algorithms are selected for their advantages in handling time series data and complex nonlinear relationships. Python's machine learning libraries, such as TensorFlow, sklearn, and XGBoost, are used for efficient algorithm implementations and flexible parameter tuning options. Finally, the real-time computing framework is described, with Apache Flink chosen for its ability to handle continuous data streams and support millisecond-level data processing and event-driven applications. Flink's core strengths lie in its low latency and high-throughput processing capabilities, enabling the system to respond immediately to market changes and update risk assessments and alert signals in real time. A risk monitoring system's data processing algorithms, including data aggregation, window functions, and pattern matching, are implemented in Flink to address various risk scenarios in financial markets. These algorithms are integrated with a comprehensive RESTful API, enabling efficient and secure interactions between system components and external systems. The API provides extensive access to system functionalities, facilitating seamless data exchange and analysis. The experimental setup utilizes financial market data from January 1, 2010, to December 31, 2023, divided into training and testing sets with an 80-20 split. A rolling window approach is employed for model training and testing, with an initial training window of 5 years, a prediction window of 30 days, and a rolling step of 30 days. The long short-term memory (LSTM) model is configured with 128 hidden units, a batch size of 64, a learning rate of 0.001, and the Atom optimizer. Early stopping is implemented with 100 epochs, and hyperparameters are tuned using 5-fold cross-validation. Evaluation metrics include accuracy, precision, recall, F1 score, and AUC/ROC area under the curve. A comprehensive evaluation of LSTM, random forest, and gradient boosting trees models is conducted, comparing metrics such as accuracy, precision, recall, and F1 score. The results indicate that LSTM slightly outperforms the other models, achieving an overall accuracy of 87.5% and an F1 score of 0.86. Random forest and gradient boosting trees perform similarly, with accuracies of 85.3% and 86.1%, respectively. Notably, LSTM excels in identifying market crash risks, achieving a recall rate as high as 92%. Basic statistical information of the dataset is provided in Table 2, offering insights into the data distribution and characteristics. The proposed LSTM model is evaluated for its performance in identifying various financial risks. The ROC curves for different risk types, shown in Figure 3, reveal the model's proficiency in capturing long-term dependencies. The liquidity risk curve exhibits the highest area under the curve, AUC, of 0.95, while the operational risk curve yields the lowest AUC of 0.82. This disparity is quantified using the integral formula for AUC, August equals TPR, FPR, D, FPR, which integrates the true positive rate with respect to the false positive rate. The ROC curves in Figure 4 further corroborate these findings, demonstrating the model's ability to distinguish between different risk types. Notably, the LSTM model excels in identifying liquidity and market risks, with AUC values of 0.95 and 0.92, respectively. In addition to model performance evaluation, a system efficiency analysis is conducted to assess the system's processing capability under varying data scales and concurrency conditions. As data volume increases from 100 GB to 1 TB, the system's processing time moderately increases from 15 minutes to 78 minutes, while maintaining a relatively stable throughput of 1.2 GB per minute, as illustrated in Figure 6. The optimal balance between processing time and throughput is achieved at a data volume of 500 GB, with a processing time of 42 minutes and a throughput of 1.3 GB per minute. Furthermore, the system's performance under high concurrency is evaluated, with the average response time increasing moderately from 0.5 seconds to 1.2 seconds as the number of concurrent users increases from 100 to 1000, as shown in Figure 7. These findings collectively underscore the effectiveness of the proposed LSTM model and system architecture in identifying financial risks and handling large-scale data processing. The system's performance evaluation reveals a latency of 2.8 seconds, indicating satisfactory responsiveness. Notably, the system's throughput peaks at 2,800 requests per second with 500 users, demonstrating optimal performance under moderate concurrency loads. This scalability and stability enable the system to effectively support real-time risk monitoring needs for large-scale financial data. The performance analysis charts in Figures 5 and 6 provide a visual representation of the system's concurrency performance, further highlighting its efficiency and stability. The proposed four-layer hierarchical architecture integrates large-scale financial data with advanced machine learning algorithms, such as long short-term memory, LSTM, and random forest. This enables real-time monitoring of market risks and prediction of potential future risks. Experimental results demonstrate the effectiveness of LSTM in identifying market risks, showcasing high accuracy and recall rates. By optimizing data processing platforms and real-time computing frameworks, the system has proven its efficiency and stability in handling large-scale data, providing robust risk assessment and alert support for financial decision-makers. The system leverages the strengths of big data and machine learning technologies to address emerging financial risks, consistent with previous research highlighting the importance of combating emerging financial risks in the big data era. The machine learning-based approach to portfolio risk management is also consistent with existing work proposing a portfolio risk management model based on machine learning. Overall, the system's performance evaluation and experimental results demonstrate its potential to provide efficient and effective real-time risk monitoring and prediction capabilities for large-scale financial data. Recent research has focused on integrating big data, artificial intelligence, and machine learning techniques in financial market risk management. A range of methodologies have been employed, including particle swarm optimization, PSEO, algorithms, BP neural networks, and Markov chain Monte Carlo methods, to predict and manage financial risks in the digital economy. Studies have demonstrated the effectiveness of PSO-based BP neural networks in predicting stock market trends, particularly in the context of IoT applications. For instance, a PSO-based BP neural network was developed to manage financial risks in IoT environments, showcasing its potential in predicting stock market trends. Managing big data challenges in financial markets has emerged as a critical concern, particularly with the rise of fintech innovations. Researchers have emphasized the importance of developing algorithms to manage big data in IoT-based fintech, highlighting their potential in enhancing financial risk assessment and prediction. Optimization approaches, such as those utilizing computer data simulation and Markov chain Monte Carlo methods, have been proposed to improve financial market risk prediction systems. Machine learning techniques have also been leveraged to develop big data-driven IoT systems for credit evaluation and early warning in finance. These systems have shown promise in improving risk assessment and decision-making processes. Advanced analytics have been recognized as a crucial component of financial management strategies in the era of big data, with applications in machine learning, optimization, and risk control. Surveys have highlighted the growing importance of machine learning in financial market surveillance, while studies have employed machine learning approaches to evaluate excessive financialization risks of trading enterprises. Optimization of economic management modes and risk control based on big data has also been explored, with a focus on improving risk control in financial markets using particle swarm optimization algorithms. Marketing strategy optimization based on financial big data has been investigated, and financial market risk has been analyzed using machine learning and PSEO algorithms. Data mining and deep learning methods have been applied to Internet financial market risk management, offering insights into the complexities of financial risk assessment and prediction. These studies collectively underscore the significance of integrating big data, artificial intelligence, and machine learning techniques in financial market risk management, and highlight the need for continued research in this field.